In this video, we are going to talk about combination of sources. See, we have a number of EMF sources. Let's consider these two. So these two are two identical sources of EMF with both of them having an EMF of 1.5 volt across them. Now I can ask the question, what will be the EMF if I connect them in series like this? And we all know the answer, that the EMF will be added up and the net EMF will be 3 volt. That is 2 into 2 times 1.5 volt. Again, I can ask what will happen if I connect them in parallel. Again, we know the answer. Both the sources are identical. Therefore, the net EMF, effective EMF across them will be the same as the individual EMF, which is 1.5 volt. In this case, the answer is quite simple because both the cells are identical. But what will happen if I connect these two cells, where one of them having an EMF of 1.5 volt, another 9 volt? If I connect them in series, the answer is again straightforward. The EMF across the series combination will be the sum of the individual EMFs, which is 9 plus 1.5 equal to 10.5 volt. But what will happen if I connect them in parallel? Will it be 9 volt? Will it be 1.5 volt? Or will it be something in between 9 and 1.5? That is rather an interesting question to ask. Similarly, I can ask another question. Observe that in this case, both the sources are voltage sources, are sources of EMF. What if we combine current sources in series or in parallel? So what will be the effective current value for the combined current sources in series or parallel? So that is the question we are going to discuss in this video. So the topic of this video is combination, which means either the series or parallel of sources, which means either the voltage source or current source. So we can have either voltage sources or we can have current sources, and we can connect them either in series or in parallel. So the question is, what will be the effect of the series and parallel combinations? So before we come to this question, let us very briefly recapitulate our knowledge, our intuition about voltage and current sources. So what is a voltage source? Let me another ask, what is an ideal voltage source? So voltage source. Let's take an ideal one. An ideal voltage source, which we denote with this symbol, is a circuit element which generates an EMF, and constant EMF across or between its two terminals. And no matter whatever current is flowing through the source or whatever happening in the outside circuit or wherever in the world, the EMF across these 2 points, across the 2 terminals of an ideal voltage source is always constant and this is a characteristic value for this ideal voltage source. Let me denote it with E. E standing for EMF, electromotive force. So this is a constant for an ideal voltage source, no matter whatever current that passes through this source. But a practical voltage source is a bit different from this one. What happens when a current flows through it? The voltage across its two terminals drops. Why? This is because all voltage sources, all practical voltage sources have some internal resistances or impedances in case of AC, so that when current passes through it, a voltage drop occurs, and thereby it reduces the effective voltage across the two terminals. So a practical voltage source is one which always has a internal resistance. Apart from the EMF of it, it always has an internal resistance Ri, so that the effective voltage across its two terminals is, if I call it as V, V is not equal to E but is less than E by an amount of I times Ri, where I is the current flowing through the source and Ri is the internal resistance of this source. So that's how we model a practical voltage source. Now let's consider current sources. Let's start again with an ideal one. An ideal current source is a circuit element which has a constant current value, or which passes a constant amount of current through it, no matter whatever is the resistance of the external circuit or whatever happens in the external world. The current through the current source, through this ideal current source, is always constant, and this constant value is a characteristic of this ideal current source. So this current stays constant, stays fixed, no matter whatever impedance, whatever resistance I connect across it. In other words, if I connect a huge amount of resistance R, even then the voltage that will develop across this resistance will be equal to, so the voltage will be equal to IR. So this voltage will be huge if I connect a huge resistance across an ideal current source, but this current will stay same, which is equal to I. So an ideal current source is one which can generate any amount of EMF, no matter however high, to pass this required amount of current. In case of an ideal voltage source, it can generate only a fixed amount of voltage, and if I connect a high value of resistance, then the current that it passes will be reduced. But in case of a current source, the current stays constant no matter whatever is the resistance or impedance is, and to pass that amount of current, it will generate any high amount of voltage that it requires to generate to pass that current. So that is an ideal current source. Now we also have a concept of a practical current source which cannot keep the current constant in the external circuit, because we say that there is an internal conductance associated to this current source. Therefore, what happens is this, the current that passes through the current source is I, but we have an internal resistance or conductance Ri, or I can say the conductance is Gi equal to 1 by Ri. Now what will happen if I connect some external resistance or external circuit Re? The current through the external circuit will not be equal to I, will be less than I, because a part of the current flows internally through this internal resistance. So therefore this current will be less than I and will be equal to I minus I internal current. Therefore, if I connect a higher value of the external resistance, then in this external circuit I'll have lesser current. Why? Because this current I stays constant, and a part of it goes through the internal resistance and a part of it goes through the external resistance. Now if I connect a higher value of external resistance, then more current passes through the internal path and less current passes through the external path. So as I increase Re, or external resistance, the current in the external circuit reduces. So that's how a practical current source behaves. Now let us come back to our original question, which is what happens if we connect voltage and current sources in series or in parallel. Consider that I have a number of voltage sources, each having an EMF of E1, E2 and up to En, all of them having an internal resistance of R1, R2 up to Rn, and I connect them in series like this. So E1, R1, so this is the first source of EMF, connected to the second one, E2, R2, and then so on. It's connected to the En, Rn. Now the question is, what is the effective EMF across these two terminals? And what is the effective resistance as seen from these two terminals or between these two terminals? In this case, the answer is known to all of us, is that the effective EMF E effective will be equal to sum of all EIs, I equal to 1 to N, and the resistance R will be equal to the sum of all internal resistances I equal to 1 to N, because all the resistances are in series and all the voltage sources are in series. So this is quite straightforward. Okay, so this is very simple. Now let's consider a slightly difficult question, which is what happens if I connect them in parallel. So this is E1, R1, E2, R2, and so on up to En and Rn. So R1, R2, Rn, E1, E2, En, all connected in parallel. So what will be the effective EMF across this? That's the question. Okay. We'll come to these answers shortly, but before that let's consider a parallel combination of current sources. Say we have current sources I1, I2, I3, so on up to In, each with an internal conductance G1, G2, G3 up to Gn, and we connect them in parallel. So they look like this. This is I1 in parallel with G1. So G1, which is equal to 1 by R1. This is I1, this is G1, then next one is I2, this is G2, so on up to In and Gn. So all these are connected in parallel. Now what will be the net effect across these two terminals? That's the question. In this case, you see that the answer is quite simple, because we can group these current sources together. They are all in parallel, I1, I2, In. So they are all in parallel. Let me redraw them like this. I1, I2, In, all in parallel between these two terminals, and see these all resistances are, or conductances, they are also in parallel, G1, G2, Gn. So they are all in parallel. So therefore, I can group these or club these current sources I1, I2, In together into a single current source in parallel with a single conductance, which is the sum of all these conductances G1, G2 up to Gn. So then this is equivalent to a single current source I equal to sum over II, and a conductance G equals sum over all Gi. I equals 1 to N, here again I equals 1 to N. Okay. So this is again quite simple, quite straightforward. Now let us consider this case. So we have seen that when voltage sources are connected in series, is very easy to find the effect of them. Similarly, when current sources are connected in parallel, it is easy to find the effect of the combination. And we know that a voltage source can be converted into a current source, equivalent current source. Similarly, a current source can be converted into an equivalent voltage source. In this case, since the sources are in parallel, if we convert these individual sources, individual EMF sources into equivalent current sources, then we'll have a set of current sources connected in parallel, and then it's easy to find the net effect of them. So that's what we are going to do in this case. Let us do this in a separate page. So let me redraw it. So I have this set of voltage sources E1, R1, E2, R2 up to En, Rn. This is plus, minus, plus, minus, plus, minus. And I'm going to convert them, each of them, into equivalent current sources. How do I do it? So this is equivalent to each of them a current source in parallel with a conductance or resistance, where this resistance is equal to this resistance R1 and this current is equal to I1 equal to E1 by R1. Then the next one, I2, this comes from this source E2 R2, this is equal to E2 by R2 R2. Similarly, I'll have Rn and In equals En by Rn. Now all these are connected in parallel Now I can combine these current values together. So then this circuit is equivalent to a single current source I1 plus I2 plus In this is equal to I is equal to I1 plus I2 plus In with all these corresponding conductances summed up. So here the conductance value G will be equal to the sum of G1 plus G2 plus Gn, which is equal to 1 by R1 plus 1 by R2 plus 1 by Rn. Now let me convert this current source into an equivalent voltage source. So what will be the corresponding voltage? So this voltage, okay, so let me first draw a equivalent voltage source plus minus so this voltage source will have E equal to I times the resistance of this, or I by G conductance, and this R will be equal to the resistance of this, which is 1 by this conductance. This is equal to 1 by G. So let me write these equations by expanding E and G. So E is I by G, where I is equal to I1 I2 In, and now I1 equal to E1 by R1, I2 equal to E2 by R2. So I can write this as like this: I by G, this is equal to sum over I1 plus I2 plus In by G. Now 1 by G is equal to R. So let me put this R here, and then I1 is equal to E1 by R1 plus I2 is equal to E2 by R2 plus up to En by Rn. Now here I have R okay, let me just write it in terms of G. So this is by G. So here I have this divided by G. Now G is equal to 1 by R1 plus 1 by R2 plus dot 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 up to 1 by Rn. So this is the effective voltage across these two terminals. That means across these two terminal, that means across these two terminal, that means across these two terminal. So if I connect these voltage sources in parallel, the effective voltage will be this sum over E1 by R1 plus E2 by R2 plus up to En by Rn whole divided by 1 by R1 plus 1 by R2 up to 1 by Rn. And if I also ask what is the effective resistance between these 2 points, it's simply this R, which is 1 by G, which is 1 by this quantity. So I can write maybe here that R is equal to 1 over 1 by R1 plus 1 by R2 plus up to 1 by Rn, which is nothing but the parallel combination of all these R's as expected. Now let me just tell you that this result is known as Millman's theorem. However, this is nothing difficult, nothing very new, nothing unobvious at all. This is just what we get if we convert a set of parallelly connected voltage sources into current sources and then combine their current into a single current source, their conductances into a single conductance, and then again if we convert it back into a equivalent EMF source or voltage source, then this is what we get very easily. So this is what is called Millman's theorem, but this name is shouldn't be a scary thing to us, because this theorem and its derivation is very simple, very straightforward. So now let me put down the result here. So this is equivalent to a single EMF source with a single resistance E and R, where E is given by sum over E I by R Ri. Okay, let me rewrite it clearly. So E is equal to sum over EI by Ri whole divided by sum over 1 by Ri. So this is E. And also this R is equal to sum 1 by sum over 1 by Ri, the parallel combination of the resistances. Okay, so this is straightforward. This is done. Now let us consider the last case, which is a series combination of current sources. Again, this is going to be quite straightforward. Let me first take a set of current sources, practical current sources, I1 with internal resistance R1 in series with I2 with its internal resistance R2, so on up to IN with its internal resistance Rn. The question is, what is the net effect of this series combination? Once again, we know that it's easier to find the series combination of voltage sources than current sources. So we will convert all these current sources into equivalent voltage sources and then find the equivalent series combination of those voltage sources, and then we will again convert that voltage source back into a current source. So this is equivalent to an EMF source minus plus this with R1. This is R1, and here E1 is equal to I1 R1. This is in series with minus plus E2 equals I2 R2 in series with R2. Then so on up to this last voltage source En equals In Rn in series with Rn. Then we combine these voltage sources together, so we get a single voltage source E is equal to sum of Ei, I equals 1 to N in series with this resistance R, which is the sum over Ri, I equals 1 to N, that is R1 plus R2 plus R3 up to Rn. So then we have to convert it back into a current source. I mean, it's not that we have to, but if we want it to be a current source, because the original problem was with current sources, and if we want an equivalent current source, we can convert it back into a current source. Then the equivalent current I will be E by R, and the resistance will be R, this R, right? So finally I can write that E is equal to E by R, which is equal to sum over Ei, I from 1 to N divided by R, which is sum over Ri, I equals 1 to N, and then this is equal to, so individually Ei, there are I, so I can write it as Ri, I equals 1 to N divided by this sum over Ri, I equals 1 to N. And then this final resistance R is nothing but the sum over Ri, I equals 1 to N. So let me just put this result back here. So I have I is equal to sum over Ri divided by sum over Ri, and R is equal to sum over Ri. Okay. Now let us consider an example problem. Which is as follows. Okay, before coming to that example, let me just state a fact that the results derived so far in this video can be generalized. So the results derived so far can be generalized for AC by replacing resistances with impedances and the values of the EMF, they will be vector quantity or phasor quantities having both a magnitude and a phase, both in case of current and voltage sources. So the derivations remains exactly same as before. Only thing we have to do is replace the impedance resistances by impedances and the DC voltages or DC currents by phasor voltages and phasor currents. Now let us discuss an example. Suppose I have a three-phase alternator, three-phase AC source. So I have a three-phase alternator AC. Let me call it as A, B, and C. And this is feeding a three-phase load. Let me call it as ZA, ZB, and ZC, and the load is not necessarily balanced. The load is unbalanced, and the neutral point is not connected. So this neutral is earthed or grounded here, but this start point of this star connected load is not grounded. So it's not necessary that that the voltage at this point is equal to 0. Now if we ask the question that what is the current in this lines, IA, IB equal to what, and IC they are equal to what, or what are these load or phase currents? Or if I ask what is the voltage at this start point, if we apply the Millmans theorem, then it becomes very easy to find these answers, because you observe that this voltage source is, and this impedance ZA, let me call this, okay, EA, EB, and EC. So this is like EA is equal to sum E with angle 0 degree, EB is with same magnitude but angle minus 120 degree, and EC same magnitude, angle 120 degree. So EA, EB and EC is known, is given, so this is known. ZA, ZB, ZC is also, are also known. Now let's consider this EA together with ZA, EB together with ZB, and EC together with ZC. So let me just redraw this slightly differently. So EA, ZA, then here I have EB and ZB and EC and ZC. So this is the ground point and this is the star point, but this is not grounded. But see that these three sources with internal, if we think this ZA, ZB, ZC as kind of their internal impedances, and it need not be their internal impedances, I mean impedances in series with them, then applying Millman's theorem, it's straightforward to find the voltage at this point. If I call this voltage as V, then Millman's theorem tells me V is what? V is nothing but a kind of average of these things, EA by ZA plus EB by ZB plus EC by ZC whole divided by 1 by ZA plus 1 by ZB plus 1 by ZC. So V can be computed directly. Now once I know V, then I can compute these currents quite easily. For example, this current is IA, then I know that here the potential is 0, here the potential is EA, and then here the potential drop is EA times ZA. Therefore, V, the potential at this point, should be equal to EA, the potential at this point, which is EA, minus the potential drop from here to here, which is IA ZA. Therefore, I can compute IA as V or EA minus V. EA, I take V there on the right side. So EA minus V divided by ZA. So this is what IA is. And similarly, I can compute IB and IC. This becomes very easy if I use this Millman's theorem. Now, I would like to give you a trick about how to remember, how to not forget the Millman's theorem. Okay, so here is a trick. This is a very useful trick, I would say. How to remember Millman's theorem. So this is very useful, not to forget it ever. Okay, so if I have E1, E2, up to En the voltage sources with internal resistances as R1, R2 up to Rn, and I combine them in parallel, then the effective EMF E will be weighted average of E1, E2 up to En. What is an weighted average? Okay, before that, what is an average? So if I say average of E1, E2 up to En, this is given by nothing but E1 plus E2 plus E3 plus up to En divided by N. So this is average. So all EMFs divided by the number of the terms I have. Now what is an weighted average? Weighted average looks like something as follows. It can be like this. Some W1 times E1 plus some W2 times E2 plus so on up to Wn times En divided by the sum of all weights W1 plus W2 plus W3 plus up to Wn. So it's nothing like okay, consider that how we compute the grades for your final grading, for your final scorecard. So if we take say 5 class tests, and if your marks for those class tests out of 10 is like say 8, 7, 9, 6 and 10, then the simple average is this, is given by 8 plus 7, 15 plus 9, 24, 30, 40. So 40 by 5 is equal to 8. Now I may decide that this class test, the first class test was difficult, and maybe this class test was easy. So I may like to give more weightage to this last class test and give maybe less weightage to the first class test to be fair to your scoring. So I can do it like this. Then a weighted average can be something like this. I can give say less weightage to this, something like 8 times 1, give more weightage to this one, so 10 times say 3, and some medium weightage to this class, something like 7 times 2 plus 9 times 2 and 6 times 2. Then I have to divide it by 1 here plus 3, 1 plus 3 4 plus 2 6, 7 8 9 10, divide by 10. So this becomes 8 plus 30 plus 14 plus 18 plus 12 divided by 10, which is like 30, 44, 74 plus 8, 82 by 10 is 8.2. So this is your weighted average. You get better score with this weighting scheme. So this is how the weighted average looks like. So the individual numbers are multiplied with some weights, and then it's divided, the entire sum is divided by the sum of the weights. So that is how a weighted average is. And in case of the Millman's theorem, these weights are nothing but the corresponding conductances. So here the weights are the conductances. So like W1 is 1 by R1, W2 is 1 by R2, and Wn is 1 by Rn. So EMF is, so the parallel combination is equivalent to the weighted average of these individual EMFs, where the weights are the corresponding conductances, internal conductances of the individual cells. So in summary, Millman's theorem can be written as E effective is weighted average of individual EMF with weights equal to conductances, internal conductances. So this is Millman's theorem. Effective EMF of the parallel combination of these individual EMFs is nothing but the weighted average of the individual EMFs weighted by the corresponding conductances. That's how you may remember it. Similarly, for the series combination of current sources, let's go back to the result. So here we have the effect of series combination of current sources. Here we see that again the final current, effective current, is an weighted average of individual currents where the weights are resistances. So weights are here, weights equals resistances. So in case of current source, weights are resistances. In case of voltage source, weights are conductances. That's all you have to remember if you want to remember this formula. So we have derived Millman's theorem, or we have seen how to combine voltage sources in parallel and current sources in series, and then we have seen an example of a unbalanced three-phase load connected to a star-connected supply, and we have seen that using Millman's theorem, it becomes very easy to find the voltage at the star point and all the individual currents, and it's very easy to solve this circuit using Millman's theorem. However, even you can solve this circuit using without using Millman's theorem, maybe using your favorite mesh analysis or nodal analysis. That too is fine. You can get the same result using mesh analysis or nodal analysis. In fact, Millman's theorem is not different from nodal analysis at all. So okay, so let me show you an alternative derivation of Millman's theorem. So previously we have converted voltage sources into current sources and then combine them and then again convert it back the effective current source into voltage source. Now let's derive the same thing in a slightly different manner. The result will be same. The same thing you can derive in many different ways. So let me do it like this. Let me apply a nodal analysis on this. So this is E1, R1, E2, R2 and En, Rn. Okay, so if I want to apply a nodal analysis, I have to take one point as my reference or ground. Let me take this as my ground or reference. So the potential here I assume to be 0. And then there is only one another node. Let me take this node as the potential at this node as V. Now if I apply nodal analysis, so nodal analysis tells me that the sum of the currents entering at this node is equal to 0. That's the KCL. So let me apply KCL at this point. Let me call it V. So if I apply KCL at V, so what is the current flowing here? Okay, this I1, let me call it I1, let me call it I2, and let me call it IN. So KCL says that I1 plus I2 plus up to IN is equal to 0. Now I1 is what? Okay, so this point is at 0, that means this point is at E1, this point is at a potential of V. So the potential difference between here and here is V minus E1. So the current I1 will be V minus E1 divided by R1. Similarly, this is at 0, this is at E2, this point is at V. So the potential difference across this R2 is V minus E2. So the I2 will be V minus E2 by R2 plus so on. This one will be V minus En by Rn. This equal to 0. Now this implies that V, if I take V as common, I have 1 by R1 here plus 1 by R2 here plus up to 1 by Rn. Then all other terms, like this, let me take the minus common, then I have E1 by R1 plus E2 by R2 plus En by Rn, this is equal to 0. So which implies that V is equal to E1 by R1 plus E2 by R2 plus up to En by Rn, this quantity divided by this coefficient of V, which is 1 by R1 plus 1 by R2 plus 1 by Rn. So we have derived Millman's theorem in a different manner using KCL or nodal analysis. Similarly, in the case of the series combination of current sources, you can have an alternative derivation without converting them into voltage sources. So let me summarize what we have done. So we have discussed the combination, series and parallel combination of sources, current sources or voltage sources. We have briefly recapitulated the behavior of an ideal and practical voltage source, of an ideal or practical current source. We have derived Millman's theorem by source conversion. and we have also seen an example of an unbalanced star connected load connected to a star connected three-phase supply, and using Millmans theorem we have derived the phase currents and the star point voltage quite easily. We have given you also a trick, very useful trick about how to remember Millman's theorem, by remembering that the effective voltage of parallel combination of EMF sources, voltage sources, is just an average and weighted average of individual voltages, where the weights are the conductances of the internal conductances of the individual voltage sources. Thank you.